Hello?
Hey, good evening, everyone. Hey, welcome to our Central Maryland meetup for this month. I'm Greg Starkey. I'm the technical director of Booz Allen's cyber account here in the area, and I'm glad to see everyone here. We're trying something a little different today. This subject is so important to some of our extended enterprise folks. We're trying to stream this through YouTube out to Georgia, Texas, and Hawaii. So thank you, Jailbreak, for trying to make this happen. Who knows? But let's give it a try. So let's see. Last month's meetup was Anat Kashiva, and he did a talk on internet paranoia. I haven't turned on my computer since. But he has a set of slides that were in high demand. They're on the meetup site if you want to see them. He has lots of references to all sorts of things that you probably should be doing and products that you probably need. But if you can't get it down off the meetup, we can send you the slides. So just talk to Lauren over here, and she can help you get the slides. Okay, today we have a special speaker from NVIDIA. Brad Rees has been around here for a while. We all have worked with him in various ways, in various architectures. Today he's going to talk to us about GPUs and Python. So over to you.
We just got to take one up. Here.
And now? Okay, thanks everyone for coming. So I'm Brad Rees from NVIDIA. We have two other NVIDIA employees here, Larry and Rob. So any questions, you can ask them. I know nothing. So just a couple quick notices. The presentation is a combination of slides and then actual code that I'll be going through. So if anyone's ever demonstrated live code, you know it never works. And I borrowed this laptop from Larry yesterday. I put my stuff on it, the whole thing bricked, and I panicked, and I don't know, it's been flaky every day. So there's always something that could go wrong. The code is running on the laptop and not on a beefy workstation. So I picked data set sizes that, you know, they take some time on the laptop, but not so long that we all get bored. Which is, you know, typically when you want something to run, you want it to run fast. I have to show that something is slow so we can show what the comparison is with GPUs. There's also no guarantee that my code is perfect or can't be improved. I am not really a great Python developer. I've been bouncing around between so many languages that I just get confused with syntaxes and what goes where. I found this great XKCD kind of, well, one slide from it, you know. This is the ugliest mess of code I've ever seen. Back in my younger days, I did a lot of Kung Fu, and I remember my teacher came over to me once and said, "I'm not going to say what you are doing is right or wrong because I have no clue what you are doing." After that, he just like turned and walked away and went on home, and basically class was over that day. Please ask questions as we go. As I'm going through the steps, coding things up, hitting a run, if you have questions, raise your hand, you know, shout something out. Everything's in a Jupyter notebook, so I can add new lines. We can try things out. I am happy to show you how easy it is to break all this stuff, or we can go down new paths and come up with new kind of explorations of the data. One of the big questions I get asked all the time when NVIDIA goes to conferences is, why is NVIDIA here? You know, everyone knows NVIDIA from gaming. So are there any gamers out there? Yay. So we do a lot of gaming. We have GeForce Now. That's what people know us for. So we go to conferences and we hear, you know, you're a gaming company. Why are you here? Other spot that we're known is in ProViz. There's a, if everyone can see that, that's from Deadpool. Great movie. NVIDIA's actually, well, NVIDIA hardware has been used for the past 10 years in all the major movies. So any movie that you see winning awards, all the special effects is being done on NVIDIA GPUs. We do a lot of stuff with VR. Hopefully we can start doing more machine learning and data mining inside of data, which would be totally cool. And of course, self-driving cars. So that's what people typically know us for. And this screen resolution is off a little. But all those things take a tremendous amount of compute power. If you want to generate a game that's, you know, 100 frames a second on a 4K monitor, that is a lot of processing going on. And people realize that that same amount of processing can be used for other things. And that's where our Tesla kind of line of hardware comes from. So this is made for the data center. So you're taking all that compute power, putting it into kind of applications that don't have any video out. They just crunch numbers. And lately, the company has been focusing more on kind of the data center platform, and that acceleration of speed is like trickling down now over to the game side instead of the other way around. Actually, I have a copy of our latest Tesla card if you want to see it after the talk. So why does performance matter? Especially for data science. You know, data science is actually the exploration of data to find novel kind of insights and discoveries. If I give you a bunch of data and I say, I want you to do random forest and find X, you're not really doing data science, you're just coding up what somebody told you to do. So with data science, you have to get out there and explore your data. It involves knowing a lot of different things, you know. There's no easy button, you just have to do it. And this whole concept of fail fast needs to be embraced. You need to be able to go down paths and explore them, see if they work, don't work. Years ago, I was working on an effort. Actually, Mary Ellen worked on that project with me. The algorithm was wrong, but the data that came back, the analyst is like, that's what I was looking for. And we're like, yes, but this isn't right. But they wanted to productize it, and we're like, nah, just because it randomly hits something good doesn't mean that it's right. And you need to be able to explore all the paths so that when you have something ready for production, it is good, quality, repeatable, comes up with the right answer all the time. So the faster you can explore your data, the better. If you only have a 1 week to get an answer and your algorithm takes a week, you're never going to come up with something good. So we're here to talk about Python. Python is great for data science, machine learning. There's tons of packages to go into it. It's easy to use, all the things you're looking for. The problem is Python can be slow. And I know you can say, there's things like scikit-learn that actually accelerate stuff. A lot of that is written in C, and then you put a Python wrapper on top of it. We were doing that for quite a while with PyCUDA, so all the CUDA stuff is wrapped in Python. You can just embed that in there. But that really doesn't address the answer because it's just kind of a layer across it. So we really want to try to figure out how to make Python better. So enter GPUs for the win. We're here to make things better for you. So not only is the government here to help, NVIDIA is here to help as well. So last year we formed, the GPU Open Analytics Initiative was formed. NVIDIA was kind of a member in the room with them. So it was a bunch of companies. MapD is an in-GPU memory database. BlazingDB is also GPU enabled, splits across GPUs and non-GPUs. Anaconda, everyone should know Anaconda if you do Python. It's actually Continuum, but they realized that everyone just knows them as Anaconda, so they've changed their name to Anaconda. H2O makes machine learning algorithms. They have now embraced taking all their algorithms and migrating them over to GPUs. So you have H2O for GPUs. Gunrock and Graphistry are graph-based kind of analytic machines. Gunrock is a whole suite of algorithms for doing graph processing. You know, PageRank, shortest paths, breadth-first searches. Graphistry is for displaying. With Graphistry, you can display 100,000 nodes, links. It takes about 10 seconds to display that. So if you take some of the tools you're used to, Renoir or something like that, and you put 100,000 objects into it, it's not going to come back. With this, it comes right up and you can manipulate it very fast. And all that runs across a common GPU data frame layer. Unfortunately for this talk, because of the amount of time, I'm really not going to talk about the database side or the graph side. I'm just going to focus on the core analytic piece. I'm working with some of the other NVIDIA folks to develop a course that covers everything. That will probably be 4 hours or more long. So maybe once that's done, you know, Greg can host an all-day thing and we can go through it. Also in this talk, I'm not going to talk about how you install packages, anything else. So hopefully you understand how to do pip install or download things. So one of the problems is that all the packages currently talk different languages. If you want to go from Spark into Cassandra or into anything else, you always have to do data conversions. And data conversions can be time consuming. So everyone is slowly moving to this Apache Arrow foundation or framework. Arrow is actually being implemented inside the GPU data frame, but also Spark and a bunch of other people are moving to it. Pandas is all being redone in Apache Arrow. So Wes McKinney is doing a great job of getting everyone pushed in a single direction when now we all speak the same language. And this makes it easier for your machine learning algorithms to read in something, write an answer, and then the follow-on process, pick it up and do something with it. And kind of the overall ecosystem, you know, we have the training stuff at the top, TensorFlow, Anaconda, Numba, and then kind of this data frame layer that goes across it. And then everything else resides in databases. If you get a chance, play with MapD. If you love doing things in SQL, you can dump your data right in there. It's all GPU enabled, so you can do incredibly fast SQL commands. So you can group, sort, filter, manipulate your data. So let's jump into some code. Can everyone see that? I heard a maybe. How about that? Okay. So this first line really just loads the automatic timing feature. I didn't want to, I could use time it, you know, do a start and end timer around everything. I could do ampersand or percent time, and it would run the system time, but they get in the way of the code. So this is a nice little thing which automatically times every line. So the first thing you always do is you import all your standard packages. For this example, I am going to use just random data. And this is actually roughly a 3 gig file that I'm going to load. It's going to load it, convert it, and then scale the numbers. So it's random numbers from -1 to +1. I'd rather have a larger range, so I convert it to a 32-bit and I scale it by 200. It will take, it takes a little while to read it all off this disk. And so if you were doing direct loading from this right into MapD, it is a lot faster. because it does GPU direct. You know, when I ran this demo earlier today, it didn't seem to take this long. And this is one of the things where I said I had to pick data sets that were big enough to show that it was taking some compute time, but not too big that people would get distracted. So, 41 seconds. What I go through then is I'm going to create another array that's just empty. Since it's empty, it doesn't take that long. I'm now going to look across my data, compute the mean standard deviation. So I'm creating a function which will go through and normalize all my data based on this. This is a standard normalization. And I know you're probably saying, hey, there's probably a math library that already does this. What's inside of this function can be anything. I just picked something that people could easily understand and see and like, okay, I know what you're doing here. Basically, it's just subtracts the mean divided by standard deviation, and now I know how far everything is off from the mean. So that's my function. When I run it, it's now stepping through. This is 13 billion records, so it's just chugging through, single-threaded because it's Python. I have a for loop right now just because I want to just do the demo part. But yes, I could do it without the for loop. Again, I wanted something inside the function. Later on, it doesn't use the for loop. And if you say, hey, why don't you do something else in there? I can manipulate the data any way you want. I could do, you know, square of everything. Any questions so far? So imagine you're a data scientist sitting and running these things at your desk. Every now and then something takes a minute or so is nice because you can get up and, you know, go to the bathroom, get something to drink. But if every step you do takes this long, eventually you just get bored. When I work on data, if it takes more than a minute, I'm already hacking the next line and I'm forgetting about what this actually does. So it takes a minute and 16 seconds to run through all the data and do a simple normalization. And just for fun, I print out the top 20 records to show that it did something. So now let's show what we can do with Numba. So, simple import. From Numba, I import JIT. I'm going to create a new empty array just for fun. So I'm taking the same function, adding a single decorator at JIT. I name it differently just so I can keep track of it in case you want to bounce back and forth. But if you look at the code, exactly the same. And now we're going to call this. Any guesses on how fast it's going to run? Minute 16 down to. So this is a laptop with a GTX 1070. So it has 8 gigs of memory. It's a Pascal, so it's a generation old. Well, let's hit run. And it's half a second. So a little bit faster. Fast enough that I can go through, do it, and not get bored. And I print out the answers. They all look the same. So I could also do it as a vector. So I import vectorize. Again, I want another empty array. So in this case, instead of just at JIT, I say at vectorize, return type, what the input types are. This is now actually called for each item inside my array. So underneath the covers, it's breaking the array up into lots of individual calls. The syntax is a little bit different. So I have my return type equals the function. I hit run. And, whoops. I have to define my function first, and then I hit run. In this case, it's slightly slower, but not by much. It's still significantly faster than the CPU version. So from a minute 16 down to not even 1 second. And then I print out all the answers so you can see all the data across the 3 versions to see if they're the same. So by taking just one simple import, one simple declarator, you can now speed up just about any function. And I say just about any because it's very easy to write functions that are non-parallelizable. Anything where the answer to one kind of iteration is dependent on the previous answer, you really can't parallelize. That's all serial. So, but in most cases, if you have a nice loop in there, you can just do @JIT in front of it. Boom, suddenly everything is faster. Under the covers, it's creating CUDA code, moving your data from the CPU to the GPU, running it and moving it back. And you don't even have to know about that, care about that. You just have to say, hey, this is a lot faster. So let's try one other example. This time I'm going to read in a slightly smaller file, just so we don't have to wait so long. So this is only, well, I think this is still like 10 billion. So still a lot. So I convert from pandas back into a NumPy array. I define 2 functions. One scales my data. One does the normalization. Right, so scaling just takes whatever the field is, multiplies it by a number. The other one does the normalization that I just talked about. So in this case, I'm going to scale all my data by 200. So I have a range from -200 to +200. Whoops, so I was wrong. It's 13,421,000 and something. So it's a lot of data. Not really big data, but for a laptop, it's a lot of data. Again, compute the mean, standard deviation. I normalize it. I print it so I can make sure it's correct. What I'm going to do now is I'm going to go through and for each bit of data, I'm just going to run a floor command on it. And that way, it will actually convert all the data to what the standard deviation is. Just so you can show, you know, I could have rounded up, down. I just picked floor. You can pick anything else. So now I want to see what my distribution of data, whoops. Oops, ignore that command. So what I'm going to do now is convert. Oh, okay, what did I do wrong here? You know? Okay, this is one of those things where it worked earlier. Right. Whoops, I have to convert. Yeah. Let's see. I want to convert this into a pandas array. No, this was working. I swear, I had this working earlier today. And now I can't, unless I pick the, nope. Uh-oh. So the problem is that I am trying to import a pandas array, but I have a NumPy array. So now you get to see me code. Wow. I'm going to blame Larry, say it's because his laptop crashed and deleted my code. Is it column or columns? Okay. So now I've converted my NumPy array into a pandas array. And I did that because I wanted to have a named column. Then I converted that pandas array into a Pi GPU data frame. So now all that data has been moved into the data frame. And what I'm going to do now is group based on this column called data. I'm going to do a count of what's in there. Well, a little over a second to run. And then when I print out my answer, I can see that it's a nice, distribution of data as I would expect. Most of the stuff is centered around the standard deviation, 1 out, 2 out, 3 out. So standard bell curve. I can look at this data any other way if there's suggestions. I have a nice free backpack to whoever comes up with the best suggestion. I'm tempting you with goodies. John, do you have anything you want to try? Or, I don't have that one loaded, but that would be a good one. So threading and multiprocessing are slightly different in the GPU space. So in the GPU, you can thread things. Typically, you're given all of the cores in the GPU. The current kind of Volta series, the V100 has 5,120 cores. So you can start about, 1,024 threads per core. So you can have a lot of threads running. So basically, in this case, each bit of data is assigned its own thread, and there's a scheduler inside the GPU that handles starting them up and running them. You don't have to do that yourself. If you want to get down there and really get into the code, you have to write everything in C, and then you define what they call the warps, and you can do multiple warps, and but it's all handled in the back for you. I just want to clear all these answers. So I'm going to borrow some code from the MapD folks, even though I deleted all the MapD stuff from it and tweaked it a little bit. When I see the MapD, the CEO next week, Todd, yeah, I'm going to just say, hey, I use your demo, but not your stuff. So again, I'm loading all the basic stuff, NumPy, pandas, math, the GPU data frame. So I'm going to load taxi data, 200,000 taxi records. I'm going to take all those records and take pandas, put it into the GPU data frame. You can see that loading 200,000 is a lot faster than loading 13 billion. Printing it out just to say, yes, it is a Python GPU data frame. How many rows are in there? It said 200,000 and it actually loaded 200,000. So the data has the rate, the passengers, where you were picked up, where you were dropped off, how much they were charged, how much tip they got, time of day. And actually, Pandas has a nice thing where you can tell it to print, and it prints out nice tables for you. So what I'm going to do is group everything by lat long. So I define a function. Basically, everything you can do in Pandas, there is an equivalent function in the GPU data frame. So I can do all these group bys. So I do a group by, then I do apply map, which is the rounding of the lat long. So I go through each one of those. That's pretty quick. I also just pull down just a few things. So what I'll look at is the ratio of tip size to how much the fare was. And you had this nice cab driver that got a $160 tip on a $2.50 fare. I was going to try to figure out, where in New York this was going, and, whether or not this was some guy shuttling drug deals around, because that seems like a large tip for a small amount. So I'm only printing out the top ones where, the tip amount is extreme. So let's try some other stuff. We're going to look more at the tip ratio, do some computations. So the pickup location, tips. Now I'm going to reorder the data, again, by the fare amount. If you've done anything in Python, it's the same thing. I'm doing sort values. Pandas has sort values. Head just grabs the top, and then 2 pandas just so it comes up with a nice table. And again, I can do group by, pretty much anything. Group by pay. So I'm looking at what was the most prevalent type of paying? Credit card, cash. Let's see what it comes up with. This one takes a little bit longer. So the goal of the GPU data frame is really to emulate pandas. So everything you can do in pandas, you can do in the GPU data frame. Is everyone familiar with pandas? Do they use pandas? NumPy? So NumPy does arrays. There's a lot of things you can do in NumPy that you can also do inside the GPU data frame. The data frame allows you to import data from NumPy, write out NumPy, move back and forth. Now I'm wondering where this thing has gone. Should not take this long. GPU is really cranking, isn't it? Wow. I'm going to say that was an anomaly. But most of I know what it is, because I did not take the head of the thing, so it's printing out. It was coming up with this table of 200,000 entries, and that takes a little bit of time. But you can see most of the top stuff is all cash. You have to get down here before you get credit cards. So yeah, don't try to print out 200,000 things on a screen. It can be slow. I was playing around with one of these, and one of them was broken, and one of them I had working. So sorry about that. So the folks at H2O are slowly going through, and their goal is to take everything that's in scikit-learn, re-implement it on the GPUs, and have it out there under H2O for GPUs. So basically, anything that you can do in there, you just have to change the name that calls it. The syntax should all be the same. It should just run a lot faster. So this right here is extreme gradient boosting. So I take a time series. You use boosting to kind of improve performance and just zip through it to try to train a model to predict what the output's going to be. Hopefully this one will work, because it actually has to go down and go out to the web and download data. I'm actually going to skip to some of the later steps. But basically for machine learning, the process is you take a lot of data, you train your model on it. Once you have your model, then you run new data through it to try to see how well it scores. And the process is you train data, you look at your loss, how well it is, and you keep iterating over until your loss gets down to, 0 or doesn't improve. You take your model and then you run it. Yeah, I should not have picked something that downloads from the web. Any questions on anything? So in Gunrock, they have a programming language where you could write something like that. Out of the box, it has a lot of predefined functions, a lot of the standard things. To do something like that would be interesting, because you'd have to go in there and do a 3-hop extraction, multiple 3-hops extractions, and then push them up. It would be fairly easy to write. Each one could run independently, as long as you don't depend on results from any of the other ones. But out of the box, you couldn't do that. But there is code where you can write it and do it.
So does TensorFlow use this library, or did they write their own?
So TensorFlow itself is written from Google. Their TensorFlow GPU, that runs on top of our kind of packages. So that uses cuDNN and Nickel, so that's how they get the GPU-enabled piece of it. And we spend a lot of time optimizing all our code around TensorFlow so it runs fast. So there's a TensorFlow Docker container out there. You can download it. It's optimized for the latest version of TensorFlow, latest version of CUDA, everything you need. Yep. Great questions. Okay, so this thing is downloaded. I'm going to define what my training is. So I'm going to convert the data from NumPy to XGBoost format. This goes through and just runs a quick GPU histogram. Depth-wise, I'm actually trying to skip through to actually the serious part of the code. Fortunately, every step depends on the previous one. So just doing the scikit-learn API to do XGBoost parameters. Whoops, sorry, I'm not up there yet. This is going through and doing the CPU. In this case, the CPU and GPU times are relatively close. It's just setting up all the steps. I was trying to go through and cut out a lot of unneeded steps. But I kept crashing things when I cut out the wrong piece. Okay, so what this is going to go through now, it's actually going to go through and start training the model, and you'll be able to see the loss. Right. So it starts training, figures out how accurate it is. You can see the loss slowly going down. Keeps iterating over and over again. And it'll do this 200 times until it comes up with a nice accurate model. So if you want to train something, at the end you'll now have a model where I can say, here's new data, do a prediction of, I think the classes are, was it a bicycle, was it a person, was it something? $200 may have been too big of a number to do. but it's still training. A lot of times if you do TensorFlow or something, some of your models can take, anywhere from an hour to 1 week to a month. You really need a lot of horsepower to train some of these big models. Almost done. The loss is getting down there. So it took a minute 32 seconds to go through the 200 steps. Where is the CPU version? Okay, so now let's try the same thing on the CPU. It's running. And it will probably be, closing time by the time this thing finishes. So it's going through, training the model, checking accuracy, looking at the loss, going again and again. The loss is going down. But you can see running on the GPU is significantly slower. So even though other ones seemed like it was taking a long time, but it was only, a little over a minute, this one will be several minutes. XGBoost, so right, extreme gradient, or extreme boosted gradient descent. So any other questions? So the goal is to be able to take the Python that you normally do and just by changing the import, make it faster. So you either switch from using scikit-learn to the H2O stuff, you put the JIT compiler in there and now all your stuff automatically moves. You put your stuff into the GPU data frame and then everything you do in Pandas, you can sort, group, filter, all that stuff is extremely fast. If I had time, I would get into MapD. MapD will load data a lot faster. Once it's in the database, I can do all the standard SQL stuff, select star, select fields, group sorts. And what comes out of MapD is a Python GPU data frame. So then I can do the next stuff with it, or I could feed that right into MapD. Yeah, it's going to take a while. So if we look at the H2O roadmap, they're up to here. So they do have, single value decomposition, PCA, Kalman filtering, sorting, aggregating stuff. But over the next 2 years, they really plan to have everything done. I was hoping they would have SVM done because then I can do some training around there. I don't see anything on self-organizing maps though, John. Sorry. So this is all open source stuff. We encourage people to join, sign up, go through the code. If it breaks, submit bug tickets. Test it out, play with it, let us know how well it works, what can be improved. That one? Basically the same thing, we're trying to rebrand it. Somebody already took go.ai, so we couldn't use that one. So, any other questions? Otherwise, I thank everyone for coming out. This still isn't done. Like I said, it'll probably take an hour. Not allowed to leave? I did bring goodies, like I said. If anyone wants to come up, I actually have 2 T-shirts, a backpack, and a pair of earbuds. Earbuds? Yeah. I'll allow Greg to pick the winners of some items here. Sorry, I only had medium shirts. Oh, there you go. Oh. So, I mean, I'll be around drinking beer now, so ask me questions. Thanks.